hopefully I won't get into too technical, but please ask me for details if you like. Another thing, some of you might have seen versions of this talk, but I've tried to put at least a few things that you hopefully haven't seen yet. So bear with me, even though everything looks familiar. So I'm going to talk about a very simple question. Suppose you have a circuit analysis problem. Is that how Ryan called it? Or property of Boolean functions, or something like this. And you're trying to figure out whether a given Boolean function has a property or not. And there are two ways that you may, two situations which you might find yourself if you're doing this. One of them is a wonderful MCSP. You're given a truth table and you're trying to figure out what this truth table is. And another one, which is more like a succinct version that maybe cryptic people care about more, is you're given a circuit that computes the function and you're trying to say something about the function. It can be something like, is it a constant function? Is it truth table all 0? Similarly, is this circuit satisfiable? Is it monotone? Is it 0 and all 0 input? And already among those, you could see that figuring out whether a given circuit computes something that's non-constant, well, that's a problem with no and love satisfiability. Figuring out whether a given circuit is 0 and all 0 input, just plug it in and see. But one thing with plugging it in is that if instead of an actual circuit description, you're just given an oracle access to the circuit, it's just as easy to plug in an input and see. So it's not like it's very different to be able to see inside the circuit and have a box in which you plug things in. So here is the problem. We are given one of our favorite problems about Boolean function in a succinct representation. So we're given a function succinctly, and we are trying to figure out something about it. And the question is whether we have any advantage when we have a circuit, small circuit, computing a function, figuring out its properties, versus whether we have oracle access to the function. So there is, So the question is it ever advantageous to actually have a circuit in your hand? And I'm talking about circuit, but I'll mention other things because for some things it actually helps. For circuit, that's a good question. So one motivation for this, as far as I know, and Russell knows more about it than I do, is Rice's theorem in computability theory. So in computability, if you've taught computability course, when you teach Rice's theorem, students come to you and say, why did I have to learn all those reductions? I can just appeal to the theorem and not do all this work. Did anybody have that experience? So essentially, Rice's theorem in computability theory says, if you stare at the description of Turing machine, there is not much you can get out of it. You have to run it and see what it does. Is there a complexity analog of this? And another question with the Rice theorem, another way of stating it, is if any problem about Turing machine is at least as hard as the halting problem. Halting problem is the easiest property of language, is the easiest property of Turing machine. Again, is a complexity analog. So I'm going to stick with the version of scaling down to complexity, which was in a paper of Russell and a bunch of other people on possibility of obfuscation. And many of the statement and, well, the whole problem came from there. So the way we will translate to complexity, we will talk about Boolean functions instead of languages and circuits instead of Turing machine. Non-trivial in our setting will be, well, sometimes trivial if you don't need to see the circuit if you can just query the oracle. So to model of access, what I call clear box, not to be confused with white box, you're given description of circuit, you're trying to decide the property of a function it computes. And another one is black box, you're given an oracle access to the circuit, and again you're trying to decide the property it computes. I said oracle access to the circuit kind of on purpose because one caveat here is that the black box algorithm can actually see the size of the box in which your circuit is located. So at the very least, it knows that your circuit is no bigger than this parameter S given to it. And besides, it makes inputs to clear box and black box to be roughly the same size. Any questions, comments? Is the problem kind of clear? Okay. So we know that there are things that are hard in the black box, even for randomized algorithm. If we know there is only one place where something is a 0 or a 1, good luck finding it. So let me just quickly mention a couple of examples just to say how there is an interplay between the two settings. Testing something on an input, same linear complexity in both settings. Query an oracle versus evaluate the circuit. If you have a set of functions of exponential circuit size, those of you who like natural proofs would jump at this version, first thing that comes to mind. Then it really helps to have that extra parameter S, which tells you, which gives an upper bound on the size of the circuit. If our functions are actually really, really hard, like 2 to the n complexity, then there is the same, almost the same algorithm in clear box and black box. You look at the parameter S. If it's small, you reject. Otherwise, you have all the time in the world to construct the circuit, query the truth table in all places, construct the circuit, do whatever you like. And the third example is if the property of Boolean function is the OR of the truth table, that's satisfiability that we know and love. And most of you know more about satisfiability than I ever will. Okay. So here is a hypothesis that was stated in that impossibility of obfuscation paper. Suppose you have a property of Boolean function, which is easy to decide given a circuit. Does it mean that it's also easy to decide given the upper bound on the circuit size and the oracle access? Again, here we're talking about circuits. You could pick your favorite circuit, bounded, unbounded, fan-in, over whatever basis. Doesn't really matter as long as it's those circuits which are the hard things that we do. And another thing is that here, as you saw in the example with hard function, we really only care what happens on functions of sub-exponential circuit complexity. That said, we could still get an exponential size circuit for the function of sub-exponential circuit complexity, and we have to do the right thing on it. So, a couple of words about the previous work. The term scaling down Rice's theorem to complexity, I think first came up at Borchert and Stefan in 2000. They proved some NP hardness result for kind of a similar problem, where they essentially, if you translate it from languages, complicated languages to circuit, talked about symmetric. So when I'm saying symmetric capital F, that means that if you look at the capital F as a function of string on length 2 to the n, which are truth tables of functions, then that capital F behaves like a symmetric function of those 2 to the n length strings. So any non-trivial symmetric property F on circuits is UP hard with respect to polytime Turing reduction, and then there were a couple of improvements later. And then this is a paper that got us into it. This long list of people, but Russell was the only one here, have stated the actual black box hypothesis sort of the way we do, and they call it scale down Rice's theorem. They also show that if you replace BPP algorithm with promise BPP, then you could prove that this is false. And they constructed family of circuits which were the same as unobfuscatable family, well, if one-way function exists, such that it's always better to see the circuit as opposed to just try to access it black box way. So black box hypothesis sounds like not an easy hypothesis to solve. It various ways it implies all sorts of P not equal NP and other cool stuff. But can we at least look at it as a second interpretation of the Rice's theorem in computability, the one with the Haltian problem, and say, you know what, if any property is easy in the clear box setting on circuits, well, our favorite property is easy. And our favorite property here would be satisfiability, circuit sat. Can we say that deciding any property of Boolean functions is at least as hard, non-trivial property, is at least as hard as deciding satisfiability? So this is a quest. So the way to state is, well, if we know that if black box hypothesis is true, that is, there is no difference between clear box, black box access. We know black box access things exponentially hard. Circuit sat is exponentially hard. All the conjectures proof, we can retire. But suppose that circuit sat is exponentially hard, for example. What can we say about the black box hypothesis? Can we prove some kind of converse? Particularly, can we prove that if black box hypothesis doesn't hold, that is, there is some property of Boolean function which is non-trivial and still it's much easier to figure it out by looking at the circuit than querying the oracle, even knowing the circuit size, then it tells us something about circuit sat. So what we get is that for some class of nice potential counter examples, indeed, if we could figure out a nice property, faster on circuit than black box, then we could do something non-trivial for circuit sat. Okay. So questions, comments? So let me just. Yeah, sorry.
Question.
Yeah.
So, I mean, how does this compare with the result on obfuscation? Because this seems to say that if circuit sat is indeed hard, then the black box hypothesis is true. But doesn't it contradict? But doesn't the black box hypothesis contradict the result on obfuscation?
Black box hypothesis doesn't contradict the result on obfuscation because the way it relates to obfuscation is a promise problem. So indeed, the promise problem was already proven that if it doesn't hold for promise BPP, then if one-way functions exist, then you have an obfuscatable family. But this is a very promise problem. There is this distribution of unobfuscatable things. We don't know how to do it in a non-promise setting.
So the difference would be a problem defined on the full domain of Boolean functions as opposed to a problem only defined on a partial domain.
Okay.
There's another comment.
Well, I was just going to say, this is one, the promise in that result is pretty extreme, right? Like it's not. it's not one of these simple promises where you're just throwing away something that doesn't parse nicely, or
Yeah, well, the promise is there are those two tiny, fairly tiny classes of things, and it's either from this class and then it's a yes, or it's from that class and it's a no.
Why do you suspect that the conjecture is true?
Well, you know, strong ETH, people believe strong ETH, which says that circuit set is exponentially hard. If circuit set's exponentially hard, why not other things? You know.
But I think before you ask that question, you should say, do you actually believe that the conjecture?
Well, I believe that the reason it's called the hypothesis is, can I quote you?
Yes.
So Russell has a very great way of calling things hypothesis. Sometimes a hypothesis, if resolving it either way, is interesting.
I meant the conjecture
So-
about the relation between the black box hypothesis and the circuit set.
Yeah.
Very specific.
Oh, okay. So why do we believe that there is a relation?
Yes. That if something is easy than circuit set, this is
Well, SAT seems to just come up in so many things and be related to so many things that it's kind of natural to see it popping up here as well. And indeed, we could establish a connection in some setting. Besides those earlier results for Turing machines and such, they proven p-completeness by reducing SAT to kind of an earlier version of this problem. So, yeah, SAT does show up there. Yeah.
So I guess one reason we think it might be true is, I think you'll show that it's true for, or some version of it is true whenever the property is sensitive.
Mm-hmm.
And there's also the sensitivity conjecture, which implies that things that aren't sensitive have small decision trees, which is pretty close to being polynomial time with an oracle.
Yeah. So, now that you've had the synopsis of my talk from Russell, yeah. So, does this answer your question? Okay. So let me just, with all the people talking about MCSP, I figured I have to say something about MCSP as early as I possibly can in this talk. So imagine that your property is some kind of version of succinct MCSP. Succinct meaning that rather than getting the whole truth table, you may get a circuit and ask, is there a smaller circuit computing the same function? So here is a way of get circuit SAT algorithm from a BPP algorithm solving succinct MCSP. Just take a random string on fresh variable, just big enough that 2 to this number of variables over n is bigger than the parameter for which you're trying to determine the circuit size. The parameter t from MCSP. Now you have a circuit C on different set of variables for which you try to show satisfiability. Now you end those two things. Two things can happen. Either your circuit is unsatisfiable, then the whole thing's unsatisfiable, then is computed by something of size, whatever, 0 or 1, whatever you want to count, but tiny. Or your circuit is satisfiable, in which case you actually have to compute your second circuit, but you randomly guessed it, and it's probably a hard function, so it probably is not really computable by anything smaller than size c to the r, which again takes you just over the parameter t, so MCSP can give you an answer. And you could see that you could do the same thing with different versions of MCSP on circuit, with gap versions and so on. It will still work. And also it generalizes, if rather than just talking about MCSP, you talk about any property which only applies to easy functions. The only thing there is you have to figure out at least one circuit for which you know the value of the function, of the property, and then you just use it the same way. So what we want to prove is if there is a property which is decidable in BPP clear box, and it requires exponential complexity in black box, then circuit sat is easy. We cannot get there, but what we can prove, if there is a property which additionally has what we call the easy sensitive instance, that is, there is a string function f, which both has a small circuit complexity, and if you look at this as a string with respect to other string, it's sensitive with respect to capital F.
I didn't understand this definition.
Okay, so thank you, Avi, sorry. So a function little f is an easy sensitive instance for the capital F if first little f has sub-exponential circuit complexity, and second, if you look at the truth table of little f, there are lots of bits in the truth table such that flipping that bit will make it lose the property.
So
we're thinking.
you want such an F?
Yes, we say,
Such an F
yeah.
exists.
You're right.
Yes, we say if there is such a little f, then we could get a circuit sat algorithm out of capital F.
Say, for example, for satisfiability,
Yeah.
what would the little f be?
Actually, do I actually have
Yeah,
it?
so
Yeah, so for parity, anything can be little, well, anything of small complexity can be little f. For OR, string of all zeros can be little f. For majority, string with half zero, well, 2 to the n over 2 zeros followed by 2 to the n over 2 ones.
This is
What is the
majority
job?
on the number of bits in the truth.
That's right.
Yeah.
Or all in the
Yeah. So those capital things, they're all in the truth table.
Here, it's the standard definition of sensitivity. We're just thinking of the function as the input and the property as a Boolean
function.
Yeah.
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 So you want the family of functions or the property of testing to have such an instance,
Yeah.
Yeah.
and that a high sensitive instance, and that it should be an easy function to compute.
That's right.
At least sub-exponential. And then we get circuit sat algorithm. So let me just, so Russell already said that sensitivity is related at least one way to randomized decision tree complexity. So if function is hard, if sensitivity conjecture is true, then we expect something sensitive to be there. Okay, so let me just quickly say what are the ingredients of the proof.
Antonina,
Yeah.
Can you go back to the slide before the definition of sensitivity, one before? Just the last part. So if you have this promise, then what do you get?
We get the circuit sat algorithm. Non-uniform, sub-exponential circuit doing circuit sat.
And I guess that the neighbors of F would also be of small circuit complexity because you
They would be of small circuit complexity. They may be of tiny sensitivity.
yeah, okay.
Like neighbors of OR, for example, they have sensitivity 1.
Yeah.
So you have two parameters there, both of which are 2 to the little o of n. How much, are there relationships between those parameters, or is it you need the second one doesn't get much better even if the first one is a lot smaller?
Well, it's mainly the second one that gives us something useful. They both plug in into Paturi-Pudlak amplification algorithm. But essentially what we need is this to be at least 2 to the delta n, and there is better result that one can obtain with delta times 2 to the n, and except in monotone case we don't know how to get things for smaller.
But that second 2 to the little o of n doesn't improve if the first, if you had smaller bounds on the size.
Not that I know of. I don't think anything changes if we go from sub-exponential to polynomial.
Right. We need
Or-
the,
yeah.
I think we need to get something non-trivial, we need the sensitivity to be considerably bigger than the circuit size.
Yeah.
So that's why one's an omega and the other's a little.
Okay.
If one was epsilon and the other was 5 epsilon, it would probably be fine.
Yeah. So I'm already running out of time. So let me just very quickly give you a picture of the algorithm. Essentially, the idea is if you have a circuit, small circuit because it's easy, which is a description of a string which is very sensitive, and you XOR it with a circuit for which you're testing satisfiability. With high probability, the satisfying assignment for the circuit you're testing will flip a sensitive bit in the circuit for that easy sensitive instance, which is here an advice. So in general, we don't know how to find it.
Probability, what is the randomness over?
So the random, we do two things. First, we permute the inputs. And second, because we don't want to flip 2 bits, we only want to flip 1 bit, we do Valent Vazirani. So the randomness is over those two.
So like circuit CI here will be, say it has only one input, one satisfying assignment. Then you XOR it with the random, you XOR the input to the circuit CI with the random string R, which basically randomly permutes the truth table of CI. So your single satisfying assignment will end up in a random location.
Yeah.
And then it's with high probability will be the sensitive location, which flips, and then you check the property. Went from 0 to 1, and that tells you. And if you don't have single satisfying assignment, you do Valent Vazirani first.
Is it okay?
Yeah, it has nothing to do with circuit set.
Well, it has nothing to do.
Is reducing circuit set to,
Yeah.
It reduces circuit set to solving whatever the property capital F is, because we are using the algorithm for that property inside of it. That's all there is. It doesn't solve circuit set, no. So one example where,
So maybe
yeah.
just to say, to understand, I mean, you might as well assume your circuit set instance has only one satisfying assignment,
Oh, yeah.
because you can do Valent Vazirani
Exactly.
in advance. So this is the only circuit set instances you care about.
Yeah.
Okay, so just by permuting the code, the inputs, you will hit a sensitive. So
Yeah.
you might as well assume that all of them, are sensitive over all inputs.
Absolutely.
Well, but then that's harder to.
But then we don't know whether the property capital F actually has a string like that.
It's almost
Yeah.
like the assumption that.
So here is one example which may be good to think about. So think about capital F as a symmetric function. Then we know that for every k, which is a number of ones, there is something with a very small description, which is just x less than k. So we have, and we know that those things are super sensitive, like length of this truth table over 2. And this polynomial size circuit, we could use it as advice. We could solve circuit set if a thing like that can be decidable in BPP, given a circuit. But there is more than that. Just yesterday, Abhishek, over there, he told me, and Mike Sachs mentioned it before, that you could get something uniform from here by doing a really clever downward self-reducibility, which gives you much more than circuit set in BPP poly or P-poly. Actually, if you could decide some symmetric property of Boolean function given a circuit in BPP, then circuit set is in BPP. And they proved a lot more than that, but I guess I'm already out of time. Okay, let me just mention one thing, which is what you asked. When do easy sensitive instances exist? It's a very, very good question for which we don't have an answer, and I hope somebody here would have an answer. Because really what we concerned with here is that we look at things that have very large decision tree on a tiny little fraction and a well-structured fraction of strings. So it's not like we look at decision tree of all shapes and sizes. We look at those palm-like decision trees, which have like only linearly or polynomial or sub-exponential few leaves, and still they have the depth, pretty much the whole thing, or well, exponential and little n. Maybe this is enough to get us an easy sensitive instance. So I'm out of time, but I still can scroll through pretty pictures. So if somebody can solve it, that would be fantastic. Can, with this assumption, prove something about existence of a sensitive instance? And we probably need to exploit the structure of a subgraph of the Boolean hypercube. So can I take just like 1 more minute?
Yes.
So I was so frustrated with not being able to do it that I actually tried to draw a subgraph of Boolean hypercube of function on small description size. So this is when I did formal because it's easier. This is when you have and or not and you start with inputs. So this is what it looks like. And if you throw in both inputs and negated inputs so that there is no strange asymmetry, you get something like this. I have prettier picture, but I don't have time to show them.
Sorry, what is the picture?
So this is the subgraph of Boolean hypercube, computable by functions on 4 variables. Vertices are truth tables of functions. And T is the number of extra gates. So I'm considering if it's an input, there are 0 extra gates. If there is like one AND or one OR, there is 1 extra gate. So you start with just the inputs. Then you AND things together and OR them. Then you AND OR again and again. And here you start getting edges, and you start getting more and more edges. And yeah, that's what.
So what do edges mean?
Sorry?
Edges. What are
Edges are just the edges of the hypercube. So when you start, like, those are not connected. Still not connected. Now, when you throw in 3 gates, you started getting neighbors. And then you keep getting more and more. Okay, so.
Okay. Now we have to end. I'm sorry.
That's it. Yeah.
Quick question while Shrikant sets up. Yes, Avi.
Is this supposed to be an analogy of Rice's theorem? So should we think of halting as a circuit start?
Yeah.
And the Rice theorem reduces an arbitrary property to halting. So where is sensitivity there? What is the...
Sensitivity sort of reared its head. I don't...
It's non-triviality.
Yeah, it's a non-triviality.
So you don't need any size. It's just
Yeah.
a non-trivial.
So if you have something trivial, it has a small decision tree complexity, so it has tiny sensitivity. So things like from your paper, they have too small a sensitivity to have a circuit sat algorithm. That's basically it. So yeah, it passes the sanity check.
So really, non-trivial should mean small, uniform, just randomized decision trees. But sensitivity is a kind of holder for that. Thanks again. Our next talk is by Shrikant Srinivasan on the